For example 5e, we're given yet another transfer function g, and we have an input, harmonic in time, frequency of 10, and what we want to do is find the steady state response for y, the output y. So what we'll do here is, as we've done on the other parts, we'll evaluate g at j omega. Omega in this case is also 10. So when I put in s equal to 10j, I get 1 plus 10j squared divided by the denominator, so that's a 10j, 5 plus 10j. When I square the top, I'm going to get 1 plus 20j minus 100. The minus 100 comes from 10j squared. J squared is a minus 1. On the bottom, I get minus 100 plus 50j, like that. So what this becomes then is a minus 99 plus 20j divided by minus 100 plus 50j. Well, as we saw back in part D, we have two options on how we can go from here. Our goal here is to break either, to break G up into its real and imaginary parts, and then find amplitude and phase, or first write the numerator and denominator in terms of a complex exponential, and then move on from there. What we're going to do is the second approach. Okay, so from here we see that the magnitude of G, the magnitude of the numerator n, divided by the magnitude of the denominator d, so that's going to be the square root of 99 squared plus 20 squared. 100 squared plus 50 squared. That number is 0.9034. The phase angle for G is the phase angle for the numerator n, subtract away the phase angle for the denominator d. So for n, it has an imaginary part of plus 20. It has a real part of minus 99. So again, be sure to put the sign with the right part of the fraction. Then we subtract away the phase angle there for d. Well, the d has an imaginary part of plus 50, a real part of minus 100. This number here is going to be in the second quadrant. Why is that? Well, just look at the sign of the real part. It's a minus. Sign of the imaginary part's plus, so that puts it there, as well as this one here, the same thing. It's in the second quadrant. So when I do my inverse tan of the first one, I get 2.942. Do the inverse tan of the phase angle for D, I get 2.678. And therefore the overall phase angle for G, the difference between those two, is a plus 2643. So therefore, our steady state response is the amplitude, which is 0.9034 sine omega t, that's 10t, plus the phase angle 2.643. I should remind ourselves that this is in radians, like this. So again, for all five of these for all five parts of this example. It all comes down to finding the magnitude and phase of a transfer function when it's evaluated at j omega, and omega is the frequency of excitation. How you go about doing that, that's really your choice. But the first step is to first do that evaluation. Get G looking like this. And the approach we looked at in the first few parts was to write that number in terms of real and imaginary parts, multiplying top and bottom by the complex conjugate of the denominator D, and then going on from there. Or the second approach that we used here was to write the numerator and denominator themselves in terms of a magnitude and a phase. And then the overall magnitude is the ratio of the magnitudes of n and d. The overall phase is the subtraction of the two. You make a choice which approach that you like, and just stick with that all the way through. Whatever works out best for you, that's what you should choose.